This is a theorem 1.5.6 from your prescribed text. This theorem we have given three linear normed spaces E, x1, x2 with two linear isometries into T1 from E to x1 and T2 from E to x2. So this is T1 and we have T2 from E to x2. So it is clear that a T2 composite T1 inverse is a function from T1e to T2e, and we have to show that it can be extended to an isometry between x1 to x2. That is, if we have to prove that if there is a mapping from x1 to x2, by definition we have to prove that if there is an element in x1, norm of that value is equal to tx. We have to show like this. Okay, so given that T1 is a isometry into dense subspace of x1, so if we are taking any element of x1, we can construct some sequence in capital E such that T1 of that element converges to y. Okay, and here we are taking some sequence xn belongs to E such that T1 xn converges to y. Now we are considering another sequence T2 xn in capital X2. So will be clearly a Cauchy sequence because we already assumed that T1 xn converges to y, and here to show that T2 xn is a Cauchy sequence, we started with norm of T2 xn minus T2 xn. Since T2 is a linear isometry, we know that norm of T2x is nothing but it is norm x. So T2 of xn minus xm can be written as norm of xn minus xm. Also we have T1 is also a linear isometry into, therefore by definition we can write norm of T1 xn minus T1 xm, and since T1 of xn converges to y and this T1 of xn minus T1 of xm will be Cauchy, that is this T2 of xn will be Cauchy. Okay, so by linearity of Ti and assumption they are isometries. Now we are defining one operator T from x1 to x2. That is, we have to prove that this T is a isometry into. Okay, so we are defining an operator like this. Ty is equal to, that is y is an element of x1, Ty is equal to an element set in x2 such that limit T2 xn. Since we know that T2 is a isometry into the dense subspace of x2, if we are taking any element from x2, we can find a sequence xn such that T2 of xn converges to this set. So we can define like this, and to show that our function is a well defined, we are taking another sequence un such that T1 un is also converges to y. Okay, so we are taking norm of T2 of un minus xn is equal to norm of un minus xn, since it is a T2 is a isometry into which is equal to norm of T1 of un minus xn, since T1 is a isometry into, and we already given that norm of T of un minus xn converges to 0, since T1 of un minus xn is equal to, here I added one term y and subtracted it, and by which is less than or equal to norm of T1 of un minus y plus norm of y minus T1 of xn by the property of norm. And since T1 of un converges to y and T1 of xn converges to y, right side converges to 0, which means this norm of un minus xn converges to 0, that is T of un is same as T1 of xn. So by continuity, norm y is equal to limit of norm of t of xn, which is equal to limit of norm of t to xn, which is equal to norm ty. We define like this. Limit of norm of t to xn is equal to ty. We define like this. And limit of t1 of xn. Now, first we prove that if t1 of xn is convergent, we can prove that this is also convergent. Hence, this limit of norm of t1 of xn is same as limit norm of t2 of xn, which is equal to norm ty. Now, we have to prove one more thing, that is we have to prove that this image of t is equal to x2. To prove that is we have to prove that t is a isometry into x1 to x2. That is we have to prove this image of t is equal to x2. So to see this, we reverse the above. That is, we are starting from some element in x2 and find xn belongs to E such that limit of t to xn equal to z, and consider y belongs to x1 with y is equal to limit of t1 xn, which implies ty equal to z as we have shown above.